Hi, everybody. It's again a great pleasure to be here for BIOB20. This is now the 5th tutorial. And on this tutorial, we're going to see the normal distribution and talking about proton gradients. So I'll jump right in the topic of today with the problem at hand. In 1951, Ephraim Racker, a researcher at New York University, discovered that the energy currency of the cell, ATP, could be generated through the chemical reactions of glycolysis, whereby phosphate groups were transferred directly from sugars to ADP. That's something that, if you haven't learned this in biochemistry, you will. But the majority of ATP is produced through another route called oxidative phosphorylation, colloquially known as breathing. Researchers set out to find the chemical reactions that produce ATP during oxidative phosphorylation, but in 1961, Peter Mitchell, a researcher at the University of Edinburgh, suggested that such reactions would never be found. Instead, he suggested that ATP was produced by the difference of pH between the mitochondria and the cytoplasm, assuming that the proton gradient was the fuel for the reaction. Okay, so the historical context of the work today is that around the 50s and the 60s, people were interested in how do the cells generate the energy. Like there's a lot of energy that's necessary for literally everything in the cell, starting from the production of proteins to replicating the genome to moving, etc. And they had already this hint that some chemical reactions can literally produce ATP. And ATP, as many of you know, is really what the cell uses to pay every reaction that requires energy. And that stands for adenosine triphosphate. So that's a nucleotide here. So in 1960, when this work starts, there's already this idea that probably the best way to generate ATP is to couple it with chemical reactions. There are some reactions that happen that produce ATP, but Peter Mitchell, kind of out of nowhere a little bit, even though that is quite well explained in his article, says, I don't think it's a chemical reaction. I think the way ATP is produced is that there's a gradient of proton because the pH, which is the concentration of protons, the pH is not the same on both sides of the membrane. So that creates a force where the protons are kind of funneled in, and as they go in, they're coupled to some kind of pump, a proton pump, that would generate ATP as it turns. So that seemed like a little bit crazy when he proposed that in 1961, but he had some arguments. He explains the arguments in the reference. A question of stoichiometry. If ATP is produced by a chemical reaction, then it has to respect a particular stoichiometry. The global equation of oxidative phosphorylation is 6O2 plus C6H12O6. That gives 6CO2 plus 6H2O. That's something that most people see in high school. That's just what is called breathing here, which would have to produce a fixed amount of ATP molecules. Okay, you see this? If this is a chemical reaction, you have an equation here for the reaction. And if every time this reaction happens, it releases some ATP, the amount of ATP is fixed. It cannot change. Like this is really always the same, in the same way as you always use 6 molecules of oxygen, molecules of oxygen to produce 6 molecules of water. There's a 1-to-1 ratio, you can't change it here. In other words, for every atom of oxygen, O, that is consumed, a certain amount of phosphorus, P, has to be incorporated into ATP. Therefore, the P to O ratio, this is the way they came to write this in the field, of the reaction is constant. However, Mitchell observed that the P to O ratio sometimes changed, speaking against a fixed stoichiometry. So it really all boils down to that. If no matter how you make that reaction, slow or fast, you always get the same ratio of incorporated ATP per every oxygen you consume, then it's credible that there's a reaction that fixes this stoichiometry. But if sometimes you see that the number of ATP you produce is not the same for the oxygen that is consumed, then it's clearly not possible that you have a chemical reaction that will produce the ATP. There has to be something, otherwise this coupling would be necessary by what we understand of the laws of chemistry. The proton gradient hypothesis does not require any stoichiometry, so it became important to measure the P to O ratios as precisely as possible. it was observed that malonate may modify the P2O ratio, but the effect was quite small. So it became important to know whether the inhibition was real or not. Okay, so you understand the context. This relatively important question in the 60s of understanding how cells get their energy, in the end boiled down to being able to decide whether or not the P2O ratio was a constant. But because there's always an error of measurement when you do this kind of experiments, and pretty hard, then it kind of boiled down to having good enough statistics to be able to tell yes, no, is the ratio different from usual when you put malonate, or is it not different? Is it significantly different? So import the data into your OR session. It consists of independent measurements of the P2O ratios in the presence of malonate. The P2O ratio without malonate was previously measured at 1.48. So here we go. You know what to do. Copy paste here that link. You paste it into your OR session. And we have the URL first. And second, we're going to use the scan data. So I remind you that scan is to import data in your session when this data is a vector. When it's a table, you'd use read delim or read table. 11 items. Nice. Question 1, run the usual checks for imported data, plot the histogram of PO with default parameters, and add a vertical red line at position 148. What range of value is the red line in? So first question, run the usual checks for imported data. What is the thing I have to do all the time when I import data? Very first thing I do always.
Head.
Someone says head. So you can do head indeed. Head PO will show you the first 6 elements. 1, 2, 3, 4, 5, 6. Okay, so at least you get an idea of what do the numbers look like? What does the data look like? Another one that you would do all the time, not just head. Length, yeah, okay. So another one is just to say, what is the dimension or the length of the data that I have imported? 11, so we knew this, there were 11 as marked by scan, but if you use another function that does not tell you how many items were read, you always check this. And if it's a matrix, what do you check if not the length? Dim, yes, the dimensions. You always want to make sure that you have read the proper number of elements. Like I said, this is always where the nastiest errors are. It's really at the interface between your data and the way you import it in OR. In some cultures, the decimal symbol is a dot, in some others it's a comma. And so depending on who put the data, then you would have either a new field or a decimal number, etc. Like there are really many possible mistakes that you can do at that level. So plot the histogram of PO with default parameters and add a vertical line at position 148. So plotting a histogram, by now it's piece of cake, everybody knows how to do it. It's the function hist. And then you just plot, you put PO between brackets, and in principle, you get a nice histogram, which is here. Okay, so this is a histogram which is a little bit kind of underwhelming because there are 11 points, so it's not very smooth. You got this very big blocky outlook here. But that's the way it is. Okay, good. We see that the numbers are between 1.1 and 1.6. Okay, for malonate, the target is 1.48. So it's going to be somewhere here. And we see that indeed, okay, the ratio did not change a lot when you put malonate. If it's 1.48 when you don't put malonate, we could see that, well, it's not going to 0.5 or 3. So I understand that people at the time were a little bit dubious to say, is this a real inhibition of this ratio, or is it just some or a statistical artifact? And then add a vertical line at position 148. What's the function to add a vertical line again? AB line, very good. AB line, Ashley said it on the chat as well. H is for horizontal, V is for vertical. So we say V equals 1.48. And let's put some color in it so that it's a bit less sad, but also that we can see it a little bit more distinguished from the rest of the histogram. There it is. That's the red line here. Okay, so I'll show the code again here. Right, so your histogram should look like that. And so in which range is the red line? In the range 1.4 to 1.5. This is this range here. And yeah, indeed, I understand that people were quite dubious. You say, if this is what you get, is this really an inhibition compared to 1.48? Some values are even higher than 1.48 when you do the experiment. So that's not even an inhibition of the ratio. This is kind of an enhancement. So you could reasonably say there is not enough reason to believe that this change of the ratio is really statistically significant. If it's just a statistical artifact, then let's not conclude that the ratio is fixed. I mean, let's conclude that the ratio is fixed, sorry, and let's reject the theory of Mitchell right away. So it is difficult to judge whether malonate really modifies the P2O ratio. We need a model for randomness so that we can build an expectation of the random spread. The normal distribution is well adapted to model measurement errors. Okay, so again, every week we're doing the same. We say, we see this, that's great, but what's expected by chance? And before we can even discuss what's expected by chance, we need to say, what do you mean chance? And so that forces us to put down our hypotheses, say, this is what I mean by chance, this is the randomness I have in mind, and now given this randomness, what did I expect? And is this particularly, how to say this, unexpected, as simple as that? Is it shocking? So we're going to assume that the measurement errors that are typical of experiments are well modeled by the normal or Gaussian distribution. So the normal distribution or Gaussian distribution describes continuous variables that are the sum of many small effects. The normal distribution is usually represented by the symbol n mu sigma, where mu is the expected value and sigma is the standard deviation. The standard normal distribution is n01. So when we say standard, we mean that mu is equal to 0 and sigma is equal to 1. We will not need the formula, but a variable x follows the normal distribution n mu sigma if and only if the probability that x is less than a value small x is that here. So that's just for your records. I don't think we'll ever need this formula in this course. Still a very interesting formula. Question 2, use the function rnorm with default parameters to generate a random sample of size 100,000 from the normal distribution. Plot the histogram using the function hist with option breaks equals 80 to make it smoother. What is the highest graduation of the x-axis? So what we're doing here is we're just, we want to see what the normal distribution looks like. And so here we go. rnorm with default parameters to make 100,000 Gaussian random numbers. So rnorm here, if I say n equals, let's say 5, I get numbers like this. And you can see that these are numbers that are close to 0. They can be negative, positive. They have the same chance of being on the left and on the right. And they're continuous. So they're not like integers like 0, 1, 2. They are continuous. So we don't want 5 of them. We want 100,000 of them. And I'm not going to just press enter, because if I do this, then it's going to be a flow of number that will never be interrupted on my screen. So since we just want the histogram, I directly pack this into the function hist. Okay, and here we go. So when you do that, you could see that the function hist returns something that's a little bit like almost a triangle. Okay, like it's not, like it's really pointy and that's not really a triangle. So the idea is, if we make these subdivisions smaller, we make a smoother histogram. so breaks equals 80, then we can get a little bit of a smoother version of the Gaussian. And it looks like that. All right, so that is the bell curve. Like goes very smoothly on top, like it's a mountain, a very smooth mountain, and then or hill, and then goes down. I'm not sure exactly what kind of bell people have in mind, but if we kind of stretch it different ways, you could see that it would actually look more or less like a flat or peaky bell. So the Gaussian of the normal is the bell curve. And that's the way you generate the histogram here with breaks AT, is really the number of subdivisions. What is the highest graduation on the x-axis? It's 4. I'll do it again with set seed, just to be sure. Okay, there will be literally no difference. Okay, the top graduation is 4. So why do I make such a silly question? Is to draw your attention that when we draw 100,000 numbers from the Gaussian distribution, the standard, we barely get anything that's above 4. Right? It's kind of 4 is already an extreme which is very, very large for the Gaussian distribution. And that comment will have its importance as we make progress through today's session. So the function R norm with default parameters samples from the standard normal distribution N0, 1. To draw from other normal distributions, one can use the parameters mean and SD to set mu and sigma. Set the variable mu to any value except 0 and the variable sigma to any value except 1. Then run the code below. So yeah, you need to choose a value of mu and sigma, which is not the standard Gaussian distribution. So I'll kind of put this a little bit higher. Here we go. So I will say mu is equal, for example, to 18.27, and sigma is equal to, I don't know, 182.7. Okay. And then I run this code here. So always the same thing. We just set the random seed, and I'm getting 5 random numbers from the Gaussian distribution with mu equals 18.27, and the standard deviation is 182.7. And those are the numbers here. It doesn't really matter what they are. It's just like, that's the way it is. The average of them is somewhere around 18 in principle, and the spread is quite wide because here the standard deviation is 182. So it doesn't matter whether you choose the same numbers as me, as long as you don't change them now. So what we're going to do is we're going to rerun. So we roll back the random generator. We set the seed back to 1, 2, 3, just like it was before. And this time we are generating random numbers from the standard Gaussian distribution. Okay, you see this? Like here, R norm n equals 5. It means that mu is 0 and standard deviation is 1. That's the standard. But what we do is that we multiply the results by sigma and we add mu. And lo and behold, we get exactly the same numbers. Okay, generating a random sample from n mu sigma is exactly the same thing as generating a random sample from N0, 1, taking the result, multiplying them by sigma, and then adding mu. And the proof of it is that R says, this is actually what I do. When you ask me that, like mean mu SD sigma, what I do is internally, I do the operation this way, because I know it's exactly the same thing. And this is why you get the same result every time. You're just calling the N01, right? Indeed, here R norm n equals 5. Let's do it again. R norm n equals 5. You can see that the numbers are here in the range around 0, as many below 0 as above 0. With 5, of course, it's not possible. And they have nothing to do with these numbers here. Okay, these numbers are much higher, much more variable. So, but if you take these numbers, you multiply them by sigma, whichever value of sigma I chose, which is 182.7. And then I add mu, 18.27. Then I get exactly those numbers, which is pretty much the same as drawing from n mu sigma. So what do you observe? What does it mean? What we observe is that the numbers are exactly identical. There's no difference between them. What does it mean? It means that you can, instead of generating the numbers from n mu sigma, you can always generate them from n01. Okay, you don't have to specify mu and sigma because you can always, after the fact, multiply by sigma, add mu, and then you get the same distribution as n mu sigma. So in question 3, x has an n mu sigma distribution. So if x has an n mu sigma distribution, then x minus mu divided by sigma has n01 distribution. That is to say, it's a normal distribution. So we can do the forward process, but we can also do the reverse process. If when I multiply by sigma and I add mu, I transform an n01 into an n mu sigma, well, when I subtract mu and then divide by sigma, I transform an n mu sigma into an n01. Okay, it's just like either you do a multiplication addition or a subtraction and division. You just invert the process. There's something to bear in mind that whenever you have a Gaussian distribution and you know the mean and you know the standard deviation, you can convert it into the standard Gaussian, and this is why it's called the standard Gaussian, by just taking the values, removing mu, and divided by sigma. Okay, that's the opposite operation of what we just did. So that's just a preamble of easy ways in which we can generate random numbers from the Gaussian distribution using the standard Gaussian instead of using every different Gaussian, every different normal distribution every time. We can decide whether malonate changes the P2O ratio with a statistical test. Yeah, of course, that's what we're going to do. To this end, we need the 5 elements. It's always the same 5. A null hypothesis, an alternative hypothesis, a protocol to collect data, a test statistic, and a decision rule. And as we've seen is that pretty much all our work every week is finding a good statistic, something that would really have a distribution that we understand and that critically distinguishes between the null hypothesis and the alternative hypothesis. The protocol to collect data is done way up front. This is something that has started years before we do the statistical test. So this is why at the moment when we do the test, we don't need to spend a lot of time on this. But at the moment when you prepare for the test, in principle, you have to think about this very seriously. And finally, the decision rule, it's kind of always the same thing. And on top of it, at the moment, as we've seen last time, number 5 is optional. The way people do it is that they just give the p-value and they say, I'm not forcing my rule on you, I'm just giving you the threshold, and you guys decide whether this is significantly different, whether you reject a null hypothesis or you accept a null hypothesis. What are the null and the alternative hypotheses? So here, going back to the problem of whether the P2O ratio is inhibited by malonate, can someone tell me what is the null the null hypothesis in this context? So it's very important to think about it, to not do a statistical test without thinking that, okay, null hypothesis H0, the P-O ratio is equal to 1.48. Definitely. I would add something. So that is part of the null hypothesis, but that is not the full story. Assuming normality distributed, yes, exactly. Okay, so the full null hypothesis is that when you put malonate, the P2O ratio is still with an average of 1.48 and has a Gaussian distribution. Why? Because there is a measurement error. Okay, the fact that this is Gaussian is just okay, in theory, when angels do the experiment, they get exactly 1.48, but we humans, we got 1.48 plus or minus the imprecision of the instrument, the imprecision of the pipetting, etc., and all these things that make it that it's kind of 1.48, but when you do it different times, you're going to get sometimes 1.50, sometimes 1.46. So that's why we assume that the P to O ratio that we measure, the one that we obtain as a human, has an average of 1.48 and has a Gaussian distribution. Does that make sense for everybody, that we assume that? So it's part of the hypothesis. Now, what is the alternative hypothesis? Again, a very important part of the process, which most people don't even think about when they do statistical tests. So the P to O ratio is different from 1.48, assuming N01. I'd say almost. So we still assume normality. Very good. We don't assume N01. We assume that it's going to be N mu sigma. So it is still Gaussian, still normal, because we're always going to keep this idea that when we do the experiments, there is a measurement error, and this measurement error kind of has the Gaussian distribution. Empirically, that's very well justified. But we're going to say that this time mu here in the normal distribution is just going to be anything, doesn't matter what, but just not 1.48. Okay, and if it's not 1.48, then indeed that gives credibility to the idea of Mitchell, which is no chemical reaction can produce the ATP in that case, because otherwise it'd be fundamentally fixed by the laws of chemistry. Okay, so to summarize, the null hypothesis is that mu is 1.48 and the distribution is Gaussian. And then the alternative hypothesis is that the distribution is Gaussian and mu is not 1.48. A quick question. If the distribution happens to be non-Gaussian for some reason, it just happens like that, so is it kind of, should we reject the no? Should we reject the alternative? What happens in that case? So after all, like we have not completely, cannot decide. We have to do replicates. These are very good suggestions. So when that happens, we are screwed. We are totally screwed because we have forced the world to be in only two possible states. Either it is Gaussian with mu equals 1.48, or it is Gaussian with mu is not equals to 1, it's not equal to 1.48. And if it's anything that happens, it's neither case A nor B, but we have to decide between these two. So we're wrong anyway. Doesn't matter what we choose, we're going to choose one and we are going to be wrong, okay? Like if it's not Gaussian, we just cannot be right. And it doesn't really matter which one we chose, we're wrong. But of course, we don't know this because we will just have made one of the two, chosen one of the two options, all right? So it's something that's actually quite important to understand about statistical tests, is that there are many ways in which you're always wrong. Like if this thing is not perfectly Gaussian, then whatever you choose doesn't matter, you're wrong. The protocol to collect data is very important here because there was a long controversy as to whether the measurements were accurate. That's what we said in the beginning, like it really all boiled down to whether the measurements were good enough. We'll leave this discussion to experts of biochemistry and focus on the statistics in that case. The mean seems like an obvious choice, so let's try it. No, I'm sorry, statistic. So now we're going to step 4. We need to choose a statistic for the test. And of course, we could say we're going to use the mean. That's the most obvious. The common approach is to design a statistic that measures the distance to the target. We therefore need to subtract 1.48 from the mean so that the statistic is close to 0 if the null hypothesis is true, instead of being close to 1.48. Okay, this is a totally standard trick that people do in statistics, is that my null hypothesis is mu equals 1.48. This is exactly equivalent to saying mu minus 1.48 is equal to 0. That's strictly equivalent. But from the point of view of making all the calculations and all the tests, it's actually simpler to have something equal to 0. So that's typically what statisticians do. The practice is even the source of the term null hypothesis, is because you have something equal to 0 in these hypotheses. Because that's the form something is equal to 0, as in mu minus 1.48 equals 0. Okay, so instead of taking just the mean as our statistic, we're going to take the mean minus 1.48. That's a simple trick, but that will say that now we expect that if the null hypothesis is right, if it's true, if it's correct, then the statistic is close to 0, not close to 1.48. And that makes things simpler. So it is easy to compute the value of the mean of the sample from which we subtract 1.48. Okay, so let's do it. So we have PO here. What about I do mean? PO minus 1.48. Yeah, that's okay. I can compute it. There's no problem at all. Like it's an easy operation for R. So that really is a statistic. I remind you that something is a statistic if you can compute it. So we can compute it, that's a statistic. So that's easy even. But why is it not possible to derive the distribution of the statistic? So now, okay, we've got a score, it's to work. It seems that it's going to be a piece of cake. We're fairly experienced now. And I'm saying we won't be able to finish today's session if we use the mean as a statistic, because we won't be able to find the distribution of the mean. Why is that? What do I have in mind? So we can try to do it. If nobody really sees it, then we get to try and find the distribution. And you'll see that at the moment when we need to actually do it, we won't be able to. But does anyone have an idea already of what is the problem? We don't have the standard deviation. Okay, yeah, that's it. At some point, if you want to sample the mean here, okay, and if we say that this mean has a standard distribution, you need mu, okay, mu is equal to 0. I mean, not mu, but let's say mu minus 1.48 is equal to 0. That's great. But if you want to make an OR norm or something like this, like I'd say OR norm here, as usual, I will say 1,000 samples. That's great. A mean is equal to 0 because I have now transformed mu into 1.48. Or I could even say 1.48 is fine. And SD equals, what do I put here? Okay, I would need, if I say that the distribution is Gaussian, normal, and I need to resample, like at random, elements from that distribution, I need to use our norm, right? But then what do I put in SD? I could put 1, of course, but that'd be false. There's no reason whatsoever that this is the right distribution. Okay, do you guys see it? That just in order to generate the null distribution, just in order to imagine what could be the mean, what could be the PO values that we get if things were just like the null hypothesis says, I can't, because the null hypothesis doesn't say anything about what I should put here. Okay, my null hypothesis doesn't give me enough information to be able to generate the null distribution. So we could have a null hypothesis that says the mean is 1.48 and the standard deviation is 1.7 or whatever that is. Okay, and then I would say, okay, well, if it's in a null hypothesis, then that's easy. I just do that and here we go. But if I reject the null hypothesis, will it be because I've got the wrong mean or because I've got the wrong standard deviation? I won't be able to tell. I have no interest in the standard deviation. Okay, that's something that's totally uninteresting for me. I just want to know whether the mean when you put maloney is 1.48. I really don't care the variation of the experiment. It depends on how good they do the experiment. It doesn't tell me anything about nature. Okay, so here, no, I stick with my null hypothesis. I don't want to specify the standard deviation because I really don't care about this. I don't want this to be all about the standard deviation suddenly, and we're going to make a decision about nature when in reality we're just commenting, making a critique on how well people did their experiments, whether they had good enough standard deviation or not. So that makes no sense. And we cannot even get one random number from that distribution because we don't know the value of SD that we have to put, the value of sigma. Okay, so what do we do? So today's session is one of the key sessions of the whole course, because many elements have been put in place in the previous 4 chapters, and at that point, I think you will be able to understand some of the key ideas that are in the classical statistical test, and these ideas are actually quite clever. That it's not just going brutally and making approximations and saying, well, statistics anyway, plus or minus 5%, who cares? No, many of these ideas are actually taking care of this kind of problem. And I think that with the knowledge that you've acquired so far, you will be able to understand really the elegance, in a sense, of the idea with which we're going to solve that problem. The nuisance parameter. In the present context, sigma is called a nuisance parameter. We have no interest for sigma, not at all. But the fact that we do not know its value, prevents us from learning what we want about mu. It's really a nuisance. There are multiple strategies to deal with nuisance parameters. One method is to find a statistic with a distribution that does not depend on them. So instead of changing the null hypothesis and specifying sigma, maybe we can be super smart and try to just find another score, not the mean, something smarter that will not depend on sigma. If it's the case, then it doesn't matter which value of sigma is in the real world, because it will have no influence on the statistic. So we'll try that. Set the variable sigma to any value except 1. Draw a random sample x and compute its standard deviation with the command x or norm sigma equals SD equals sigma. Okay, is the standard deviation of the sample x equal to sigma? So here, of course, the text of the question is not completely accurate. First, we have to generate a random sample with the value of sigma. So I have a value of sigma, which is 182.7, so I'm going to keep it. And then I take here a random sample, x, with 11 numbers. I got them here. And now the question is if I do the standard deviation of x, is it going to be equal to 182.7? What do you guys think? Well, it's easy to test. And no, it's not. Okay, why is it not? Any idea? Because it's a random sample. Okay, you have it with the mean. It's never, the mean is not exactly 0. There is some variation, some fluctuations. So there's no reason why the sampling will bias on top of it. So there's no reason why that particular value should be equal to sigma. After all, we have only 11 numbers. We compute a statistic on them, the mean, the standard deviation. So actually, there was no reason it should be equal to that. Okay, is the standard deviation of the sample x equal to sigma? Nope, not at all, and it should not. There's no reason why it should. Okay, sigma is the value of the standard deviation of the distribution, but when you sample from it, there's always fluctuations. That's fine. Divide every value in x by the standard deviation of the sample. Okay, so the way we do it is x divided by SD of x. And remember, when you divide a sample by a number, or vectorizes everything, it will apply the same operation on all the elements. So when you do this, x divided by SD of x, every element of the sample has been divided by the standard deviation of the sample. Okay, so we did this. What is the standard deviation of the transformed sample? So now we wrap it all. Well, let's call it y. Okay, the sample y is the same as the sample x, where we have divided the values by their standard deviation. And if I do SD of y, what do I get? 1. It doesn't matter which value you chose for sigma. Okay, you always get 1 when you do this. So in the video, we've seen that when you multiply something, your sample by something, then the standard deviation is multiplied by that number. Well, if you divide the sample by SD of x, SD of x is divided by that number as well, and that makes something divided by that same thing, that makes 1. So doing that operation always, always, always gives you a sample with a standard deviation of 1. And it does not matter which value of sigma you put there. So dividing a sample by its own standard deviation may be a way to remove the dependence on the nuisance parameter sigma. So that's the intuition here with this idea. Is that, okay, we don't know sigma. It's really annoying us because we can't resample the mean. But we know a cool trick, which is if we take a sample divided by its own standard deviation, then it's always got the same standard deviation. It doesn't matter what was sigma to start with, we always get the same with that. We kind of have a way to cancel out sigma in a sense. We get something that cannot depend on sigma anymore. To obtain a statistic, we will need to take the average after this operation. So generate a random sample using R norm n equals 11 and SD equals sigma. Again, sigma is not allowed to be equal to 1. Divided by its own standard deviation and compute the mean. Can you use the function replicate to generate 1,000 random means using the same process? So here we go, step by step. Random sample using R norm n equals 11 SD equals sigma. That's easy enough, copy paste. Okay, so I got 11 numbers. My sigma is pretty large, like 182. So that's why the numbers fluctuate quite a lot. Okay, what else? Maybe we give it a name. I'm going to call it X again. So that's my new sample. X here. Okay, easy. Divided by its own standard deviation. So X divided by standard deviation of X. Okay, that gives me a sample that has a standard deviation of X. And compute the mean. Here we go. The mean is 0.559, etc. Okay, that's fairly easy actually. So, well, that's good. We have an easy way now of computing a new statistic. Take the mean, but before you take the mean, you divide the sample, every element of the sample, by the standard deviation. So that's it. We're kind of done here. Or are we? Can you use the function replicate to generate 1,000 random means using the same process? Yeah, it should be a piece of cake. So we would call, for example, null distribution. Okay, and so we use, of course, replicate as usual, n equals 1,000. And what I'm going to do is to say, I'm going to put mean here divided by the standard deviation. That's great. And for x, I'm going to say I want 11 random numbers from the Gaussian distribution. I can run this, it runs, it's okay. But this is not the correct answer. Okay, there's something fundamentally wrong here with this formula. And it's not that that I'm not putting the sigma, because we've seen that it doesn't matter which value of SD I choose. So even that here is completely wrong. The two norms generate two different sets of numbers. Do you guys see this? I have two calls here to our norm. There's one here, and there's another one here. So I'm not computing the standard deviation on the same sample as the one on which I compute the mean. Every call to R norm here is generating a new sample. And that's not the same thing as saying X is that, and I'm computing, the standard deviation on X and then the mean on that modified sample, or having something where I have two different calls for R norm. These are two different samples that have nothing to do with each other. It's not the same thing. So that's not correct here. So we want to find a way to run this replicate command here with using always the same sample, not having a first random sample here for the mean and a second random sample there for the standard deviation. So that trick here, it won't fly. We need to be a little bit more cognizant of R in order to do that. So the problem is that, yeah, we can't do that because we need to compute the standard deviation on the same sample as the one on which you compute the mean. The R programming language allows us to create our own functions, which is very useful for such cases, and more generally to use the same code multiple times. Use functions for. The following example shows the syntax to compute the square of its input for defining the function square by defining the function square. So here we go. We've seen this in the video, so that should be relatively straightforward. That's the way you define a function in R. You put a symbol here, use the keyword function here that says this is a function, this is not a number. And here, this is the parameter of the function. And the fact that x was defined before is irrelevant. That's a new x if you want. It can be quite confusing. But anyway, this function says take your input argument and square it, and you're done. So of course, if I do square 1 to 4, then I got the squares of each elements individually. So that defines a new function this way. So here we go. If we want to use the replicate function, we must make a function inside for the, typically here, that's the parameter that's called x. I forgot to write it here. So that'll be expression is that. So we want to find an expression here that would force R to use the same sample for the mean and the standard deviation. The R norm is different result. I'm not sure what you mean, Charlie. Maybe you mean the same as Marco, the fact that that you're using a different R norm for the standard deviation and the mean. So define a function statistic that subtracts 1.48 to all the values of its input, then divide them by their own standard deviation, and finally compute the mean. So we take the template here for the function, and we say, instead of square, we compute a function that's called statistic, because it's going to be our statistic. And that's a function of x, the sample, and we say, first remove 1.48. So x minus 1.48 to all the values in its input. Then divide them by their own standard deviation. So, okay, x minus 1.48 divide by the standard deviation of x. I don't need these brackets here, actually. And finally computes the mean. So here we go. The mean is here of the whole thing. That's it. It doesn't complain. So that's my function statistic here. It's defined this way. Again, using the keyword function, x is not the x that we defined before. It's a new x. It's just the parameter, the input of the function. I mean, you guys are used to it. You've done math. Like when you say f of x equals whatever, x squared, x is not really a particular value. It means like for all the values, it's going to do that. And what we do is that we remove 1.48. And again, here, this is just a computational trick that we do in the beginning so that we get a value at 0 when the null hypothesis is correct, not a value at 1.48. That will make everything so much simpler for us if everything is centered around 0 than around 1.48. So center everything on 0, divide by the standard deviation. Once I've done this, the standard deviation of that whole thing is now 1. And if it's a constant, it cannot depend on sigma, like that is independent of sigma. And then I take the mean here, and okay, that now will give me a statistic that in principle does not depend on sigma. Maybe it depends on other things, but not on sigma. So far so good with the definition of the function? Yes. Enthusiastic yes. Next, use the function statistic from question 8 and replicate to generate 10,000 samples from R norm n equals 11 and SD equals sigma. Subtract 1.48, divide them by their own standard deviations, and compute the means. So that here is pretty much what the function statistic does already. change the value of sigma by several orders of magnitude, and plot the histogram every time. I recommend restricting the x-axis to the interval -2, 2, and using breaks equals 80 for aesthetics, as we did before. Does the value of sigma impact the distribution? So let's try that. Let's see this. We're using replicate. And we say n equals 1,000, 10,000. Okay. Then we say what we want to replicate is actually the statistic taken from a Gaussian distribution where we take 11 random numbers, and we say SD equals sigma. Remember, my sigma is 182 at the moment. So that's it. Take 11 random numbers, where this time I'm giving you a sigma. That value of sigma is 182. But then apply the statistic on it, which is remove 1.48, divide by standard deviation, take the mean. And do this 10,000 times. Cool. Now, put that into a histogram. Oops. With the... and we get that here. Okay. So a fairly long title for the histogram. So that's something that is centered on 0, that has more or less this shape. So because it's a little bit, again, relatively peaky, we say, let's increase the breaks to 80 to make it a little bit more smooth. And we get something that looks a little bit more bell-shaped. Okay, interesting. So sigma was 182.7. I'm going to make another window. I'm going to show you another trick, actually. If you do par mf rho equals C1, 2, you will draw 2 panels per window, 2 plots per window when you plot. The first time here, it's going to take only half of your space, and when you do hist again, it's going to plot it just next to it. So it's just a trick here. Par mf rho equals C1, 2. So par is for parameter, for graphical parameters. Mf rho, I'm not sure what it stands for, but it's just the layout of the picture that you're making. And 1, 2 says I'm going to have 1 row and 2 columns. So this is kind of a matrix representation. I'm going to change sigma to 100 times less, 0.1827. Okay, this is 1,000 times less. And now I'm plotting the same thing again. Let's see how different is it. Oh, that can't be right. And so the reason is because I forgot here that I have to say the mean is 1.48. Okay, that's a given here. So here we go again. And that's with, well, let me do it one more time. Sigma is equal to 182.7. That's the way it looks. And now if I say sigma is equal to 1,000 times less, like that, well, I can see that the distributions are pretty much the same. Okay, here it doesn't go to 1.5, and this is why the question says I recommend restricting the x-axis to the interval -2, 2, and using breaks equals 80 for the aesthetics. So we'll do it one last time, this time, as they say in the question. So xlim, remember, that's to restrict the x-axis to some chosen value instead of computing them on the go, and that'd be -2, 2, and taking the other value of sigma, plotting it again, and here we go. So now things are stuck between -2 and 2, and you can see that now it's kind of convincing that these two distributions are kind of similar. I've changed sigma by a factor 1000, and yet there's practically no difference here in the distribution of these two. And if I set the C to 1, 2, 3, you will see that they're actually exactly identical. All right, so basically, does the value of sigma impact the distribution? No, not at all. Like if we do it this way, then doesn't matter what sigma is, it really has no impact on the distribution of this particular statistic. So we can just say sigma equals 1, for instance, take the default, because no matter what value you choose, you will end up with the same result. The distribution will not change at all. Okay, time for a little break. We'll take 5. So see you again at 6:10, and we'll start again with the next section. And I'll pause the recording. Welcome back for the second hour of today's session. And we're going to continue where we left off with heavy tails. The statistic we came up with in the previous section is called the effect size. It has a name, like you take the standard deviation, the mean, you divide it by the standard deviation, and you call it the effect size. There is an Instagram group chat if anyone is interested. Yeah, so whoever has an interest in learning statistics with the group. So be careful about the private messages, guys, because they're shown in the room. So your messages are absolutely not private. So going back to the actual topic, because the more we do now, and the less you have to do this before you even start the midterm. So I'd like to make progress today. So this is called the effect size. You take the mean divided by the standard deviation, and that has a name. The statistic is called the effect size. So instead of measuring absolute differences, we're measuring relative differences. So generate a random sample of size 100,000 from the null distribution and use it to estimate the probability that the statistic is lower than -1 or greater than 1. That is to say, the probability that it is greater than 1, the statistic is greater than 1 in absolute value. So here we go. We can generate the null distribution like this now. We say that this here is the null distribution. We compute the statistic with any value of sigma. We just choose 1. Okay, so like that was 182.7 last time, but it doesn't matter what we choose. So we can as well choose 1, choose the default. Okay, so take numbers with the mean at 1.48, choose any standard deviation. I don't care because my score will not care about this at all. The distribution will be always the same. Get 11 numbers from that particular mean, 1.48. I don't care about the standard deviation. Compute the statistic, which is the effect size, and do this 10,000 times. And that's indeed my null distribution. So that works here. We have plotted the histogram before, so we get it one more time. If I'm tired of having my window which is split in two, the easiest way is I just close it. And then when it comes back, it's regenerated. Now it has only one plot on it. So we've seen that this distribution doesn't depend on sigma, on the standard deviation. That's great. And now we just have to use the trick set seed 1, 2, 3 as usual. And now we get the same null distribution. That's the true null distribution. But now there's a question with it. Estimate the probability that the statistic is lower than -1 or greater than 1. So see the distribution here. You want to know the amount of area here, which is on the right side of 1, and on the left side as of -1. So how can we do that? Any idea? To know the probability that's hidden here and hidden there. So how would you compute the probability of just the amount that's here? What's the area, an estimate of the area of the times when the statistic is greater than 1? How would we compute that? Any idea, anyone? Find the absolute value first. Okay, we can do the absolute value first, or we can do it another way. That's the simplest way, is to get the absolute value first. To go back to the question I just asked, not the previous one, if you do sum null d greater than 1, okay, you see that 45 elements out of 10,000, sorry, are here. Okay, that little area which is there is 45 divided by 10,000. I can actually compute directly the mean, which will make this division by 10,000 for me. So that here is the area which is there. Okay, and then I can do what is the mean such that this is less than -1. And so it's the area which is there. And I can do the first plus the second. But like Marco says, we can do better, we can do easier. So we do the absolute value of null d is greater than 1, because that corresponds to both cases. And you can see that sure enough, this is the sum of this plus the sum of this. Okay, that's the number of elements in the null distribution, of which the absolute value is above 1, which means that either they were below -1 or above 1. And that's like 0.87% of the elements. So that's the answer here. And this is why having something which is centered on 0 makes everything simpler. If the average was 1.48, you'd not be able to simply do that. Take the absolute value, choose 1 minus 1 as criteria, etc. Like you would always have numbers that are close to 1.47 and 1.49. Everything would be more complicated. So that's why, as a statistician, you usually say, I'm transforming my null hypothesis into something equal to 0. Then my distribution is centered on 0 here, not on 148, and that makes this kind of balancing much easier for me at the end. So the answer here to question 10 is this one, 0087. For comparison, consider what would happen if sigma were known, so that we could divide by sigma instead of SD of x in the computation of the statistic. Generate a random sample of size 100,000 in the conditions of question 10, where SDX is replaced by sigma in the calculation of the statistic. So I'm going to, what is my value of sigma at the moment? It's 182.7, perfect. So here, remember that statistic is this thing here. Ignore the bytecode. So it was computed that way. So now I can just replace SD of x by sigma, 182.7. Use the sample to estimate the probability that the statistic is lower than -1 or greater than 1. So we're doing the same thing with a modified null distribution. So like it's in the case where we knew exactly what the standard deviation is. We kind of knew it's 182.7. So what would it look like in this case? I'm generating a new null distribution to call it null x, to show that this is not really anything real. Replicate 10,000 times, that's good, but we're not doing any of this statistic stuff here. So that is now going to be regenerate the Gaussian random sample here, take 11 numbers at random, say the mean is 1.48, and say standard deviation equals sigma, we know that. And what I'm doing with it is that I am removing 1.48, I'm dividing the whole thing by sigma this time, because I know it. Like we're playing pretend, we're just assuming that we know sigma, and we take the mean of the whole thing. So that would be the same as computing the effect size, but when you know sigma for some reason. When we look at the distribution, we get something like that. Okay, so it's a fairly similar looking distribution here. But the question is not about the shape of the distribution. This says, again, what is the probability that the statistic is lower than -1 or greater than 1? Kind of the same question as before, but in case you knew sigma. Okay, like what would happen if you knew sigma? Does the fact that we don't know sigma change something? Well, let's see. Now x, we take the absolute value again because it's centered on 0, greater than 1. And you see that the number is quite small. So I need to, again, recompute that thing with, and now I get that number, 001. Okay, with the previous distribution, I got 0087, now I got 001. So the two distributions look very similar. There's almost no area here, and kind of none here. In the previous distribution, remember that there was also not a lot of elements here. And yet, with this distribution that looks very similar to the other, we have 8 times less chance of being above 1 or below -1. It's actually a very, very significant difference. So the answer here is 0011 for this one. Okay, and you can see that the main difference is that here, instead of dividing by SDX, I'm dividing by sigma, which I can do because I assume that I know it. But when I don't know it, I cannot do that. So let's go back here. Tails of the distribution. The tails of a distribution are the probabilities of the infinite intervals of the form -infinity to x for the left tail and x to +infinity for the right tail. So the tail of the distribution is all the area which goes, let's say, from 1 till 1 and up, that's the right tail, and from -1 and below. Those are the tails. You cut and then you say from here till infinity and beyond. So we see that if we don't know sigma, if we don't know sigma, we have to divide by the standard deviation. Otherwise, we can't even compute the distribution of the score. But when we do that, the two distributions are not quite the same. It's not the same thing as if we knew sigma. Okay, so dividing by the standard deviation seems to have changed something in that distribution, but not in the central area, but more in the tails of the distribution. It somehow looks like the tails of the distribution have been changed. And even though the numbers are quite small, here we're talking of 0.1% or kind of 0.8%, they make a huge difference. So why is that? It's because the events in the tails are rare, around here, but this is the rejection region of the test. Remember, like we always put the bars, like these red bars that show where the threshold is, they're never close to the center, they're always close to the tails. And so being able to compute the probabilities accurately at the tails is really the key to statistical tests. And so even if the numbers are small, you can say, yeah, it's the same thing here. Most of the information is here. Sure, but not so sure, because everything that matters for us are the atypical values. Like, what is atypical? And if you have a model of your score which doesn't have the right expectations for how extreme it can be, then you're going to make the wrong decisions quite often, actually. At that point, it is important to highlight that the empirical standard deviation, as computed with the function SD, is not a very good estimator. So we haven't really discussed at all what is a good estimator, what is a bad estimator, but for sure SD is a bad one, and we're going to see what that means right now. Set the variable sigma to any value except 1. Use seed 1 to 3 to generate 100,000 random samples from R norm n equals 11 SD equals sigma. Using replicate, compute their standard deviations and store them in a variable called SSD for sample standard deviation. Okay, so what we're playing, like the game now is, let's just generate some Gaussian random numbers. Okay, and we compute the standard deviation. And as we've said before, you don't expect to see the same number every time. There is some fluctuations, so you should not get sigma. But as usual, you expect that if you have a sample that grows larger and larger, then you will get an average estimation, which will be around the right value of sigma. So we have to replicate that process a couple of times. So replicate here, and we say n equals, let's say 10, and the expression is this one. So that gives me 10 standard deviations estimated from 11 numbers. Okay, and the like sigma, remind you, is 182. So sometimes it's kind of too high, sometimes it's too low, etc. Well, that's the game. That's an estimator, and we have some randomness. So you can't expect that you're going to be right on all the time, or even often. Okay, so these are just like what can happen if you try to estimate sigma. But we don't do it just 10 times, we have to do it 100,000 times. That's pretty long. That will take a bit longer than usual. So we're saying SSD here is that. And you see that it takes a bit. All right. So set seed 1, 2, 3 here. So the mean of SSD that I had is 178. Remember that the target is 182. I resetted the seed. So here we go. I'm recomputing SSD, and I will keep this value in my computer for later questions, like they ask. And if I compute this, it's 178 point, pretty much the same as before, and again, below the target. So now I'm going to run them without assigning to SSD. And we'll see how long it takes before I can get an estimation. Like, you know, I ran 100,000 times this. How did I say it? I meant mean. I get 100,000 standard deviations. One is it that the average of this 100,000 is above the target value. You understand it when I take the standard deviation of 11 values. Sometimes I'm above, sometimes I'm below. I cannot always hit the right value. But here it seems that no matter what I do, I always get 178 and something, which is not the target of 182. Okay, like the average is not the right one. And I can continue this pretty much forever. I will never get something that's above 182. No matter what I do, my estimation of the standard deviation on average is below the target. So that's pretty much what you would define as a bad estimator. That's called bias. Okay, what is the mean of SSD? Around 178 something. We run the simulation a few times to see how long it takes to obtain an average above sigma. Never. Like, you would just never get an average above sigma. The estimation of the standard deviation by that method is not even converging on average to the right value. As the numbers of replicates n increases, the average of the estimate given by SD does not converge to sigma. Okay, we're not really getting closer to sigma. We're getting closer to 178, but not to 182. This is an example of a biased estimator. We have used the word bias before, especially in the very first quiz that you had to answer, without really defining it. So here goes the definition. The bias of an estimator is the difference between its expected value and the real value of the parameter. An estimator is unbiased if its bias is 0. You see this? This estimator, the standard deviation, even when you do it over 100,000 times or a million or whatever, it doesn't matter. It is not getting closer to the right value. This is not even getting closer. So that's the example of a biased estimator. In general, people prefer to work with unbiased estimator for an obvious reason, in the sense that when your sample will grow larger, you have some guarantee that you will kind of box your target value and get closer. That makes sense. But in practice, your samples are never infinite. So working with biased estimators, with unbiased estimators, is not always a good idea, actually. Even though the term unbiased seems pretty positive, etc. In statistics, bias is a good thing, but it's not, the thing is that it's not the main problem. The main problem is that being unbiased is useful only when your sample is huge. When your sample is small, it doesn't care what your bias is because you're anyway going to be super far from the target. So for our statistic, the bias of the function SD is not relevant because we incorporate it into our sampling of the null distribution. So the fact that there is a bias in SD, it's fine. Like we compute the null distribution with the bias and the null distribution is correct, even if it's using some biased elements. In the end, we're going to compare things with the bias, like you make the null distribution with the bias, compute the score on the sample with the bias, well, things are comparable. But in general, it is important to bear in mind that the standard deviation needs to be correct if one wants an unbiased estimator. Bias is a form of inaccuracy that remains even if the sample becomes infinitely large. That's what's bad about bias, is that even if you kind of blow your sample to enormous proportion, when you remove the randomness associated with sampling, then you still have a difference. But this is not the only form of inaccuracy, and often it is not the major issue, as fluctuations in small samples can be the major source of error. And this is something that's kind of hard to understand for beginners in statistics, is that your sample is usually small anyway. And the problem is not that you have a bias. The problem is that your estimator is going to kind of go left and right completely at random. The problem is the variance, not the bias. So we're going to show that in a second. Using the sample SSD from question 12, give the approximate probability that the estimate of sigma is sigma 2 divided by 2 or lower. So we have sigma here is that. And so if I do mean of SSD less than sigma divided by 2, that gives me the probability that I am less than half of the target value. So that is the answer here. It's 00894. It does not matter which value of sigma you chose. The probability may appear to be small, but occasionally the estimator underestimates the target value by an order of magnitude. Okay, being a factor 2 away from the target is like, it's serious bias. It's not bias, sorry, it's serious variance. Like you have seriously misestimated the target. I'm going to go back to the kind of values that we got. As you can see here, you can see the fluctuations, right? This is like pretty big. You go from 135 in one sample to 203 in the other one. Like this is really changing a lot, the value of the standard deviation. It's a horrible estimator. In this case, the expression mean x divided by standard deviation will tend to blow up because it is divided by a small number, and the statistic will be very large, positive or negative. You see that because we have this division, and if we underestimate the denominator, then of course the numerator gets multiplied by a large number. So that is what's creating the effect size. Unlike the mean, the effect size will tend to occasionally blow up, and that will happen when your estimation of the standard deviation is too small, and that happens all the time. So the division by SD of x is responsible for the heavy tails of the distribution. The mean has a normal distribution, but dividing by it by SD of x transforms it into a student's t variable. So that here, the distribution that we've seen for our statistic is not Gaussian. It looks Gaussian, but it's not. The student distribution has a bell shape, but unlike the normal distribution, it has heavy tails. So it all comes down from the fact that the standard deviation is a bad estimator. First, it's biased, but in our case, it doesn't matter very much. More importantly, it tends to underestimate quite substantially the real value. And when this happens, because you divide by a small number, the numerator becomes inflated. And that means that when you do that, you will tend to generate either this extremely high value on the left, if the mean was positive, or these extremely high values on the right, on the left. And so here you have a sketch of what the heavy tails mean, what they look like. So the distribution in brown has non-heavy tails. That would be the Gaussian. And they look pretty much the same in this area, the heavy tails and non-heavy tails distribution. And the brown, you could see that it goes to 0 and it goes very fast. It vanishes to insignificant numbers very fast. And that is where I want to echo my first comment. When we drew the bell shape of the Gaussian, we say even with 100,000, you never go above 4 or -4. Like you're kind of boxed within 4 standard deviations when you use the Gaussian distribution. When you use the student's t distribution, anything that has a division by SDX in it, then the tails, well, you know, these two distributions look quite similar, but the tails of the green one, they're kind of, you know, sliding over much further to the right. And even though the total probability that is here is small, it is still incomparably higher than what's in the Gaussian, in the round curve. So you can make horrible mistakes because of this when you think about preparing for the extremes. If your model for the extreme is Gaussian, you say, well, there's no chance that some extreme event like this will ever happen because they don't happen in the Gaussian world. But in a student world, student T world, then extreme events, they're rare, but they do happen. And they're way more extreme than in the Gaussian. So it's really important to understand that this operation that we've done to divide by the standard deviation, it's not innocent. It's a very profound transformation from a Gaussian to something that is not a Gaussian, the student's t distribution. And I suppose that some of you know the student t-test. And that's actually the distribution of the student's t-test. Defining the threshold or the p-value is usually based on the tails of the null distribution. So it is important to have the right model, otherwise the threshold can be misplaced. We're going to see this in a moment. If you believe that your distribution is the brown one, when in reality it's the green one, you're going to put the borders for the test at the wrong place. So that's important to get this right. Using the samples created at question 10 and 11, find the thresholds at 1% for the absolute value of the statistic. What is their absolute difference? So that was the sample null D and null X. Okay, so the threshold at 1%, it was supposed to be level 1%. How do I find the threshold at 1%, at level 1%? Any idea, anyone? So I've got this distribution here. That's this one. What is, yeah, that's the function quantile, very good. Okay, what is the value? In reality, I'm going to symmetrize it here with taking the absolute value. So it's going to look like that. And I'm saying, where is the border such that there's 1% of the area on the right of the border? Well, that is quantile. Take the absolute value of the null distribution, and I want the quantile at 0.99. So the quantile of the first distribution, the one when we don't know sigma, that's the one that we're actually using, when we need to divide by SD of x, is that. Now the quantile for the other distribution, the one that I call null x, when we do know sigma, is that. Okay, and so now if I make the difference between this minus that, this gives me a difference of 0.20. So I'm going to put if I assume that my distribution is null x because I've assumed that I know the standard deviation, for example, I fixed to some value that I got, which is approximate, then I'm going to put the threshold at a distance of 0.24 where it should really be. Okay, I'm too short because I'm kind of underestimating the fact that there are these heavy tails on the right. So I would make an error of that much, and you can see that this is a big error here. 0.5 is here, 1 is here. So having a relative error which is that big would actually be a big deal in terms of where you put the threshold. So that's important to realize that like you can't just pick a value for the standard deviation and assume that you know it. You change the distribution completely. What is the absolute difference? That here is the answer, 0.2048,047. We successfully eliminated the nuisance parameter sigma by designing a statistic with a distribution that depends on mu but not on sigma. That was the whole point. The cost is that the distribution has heavy tails, meaning that it occasionally produces very large values, positive or negative. We are almost ready to conclude, but we still need to address the question of the decision rule. Here we need to revisit the alternative hypothesis and be sure of what we want. Any departure from mu equals 1.48 is sufficient to reject the null hypothesis and to conclude that the P to O ratio is not fixed by stoichiometry. You get this, it doesn't matter if when I put malonate mu is 1.5 or if it's mu equals 1.4, it doesn't matter. Both ways that rejects the possibility that this is a fixed constant by stoichiometry. So we reject if it's too high or if it's too low, not just in one case. There are two ways for the null hypothesis to fail, either because the observed statistic is too high or because it is too low. The simplest way to achieve this is to take the absolute value of the statistic, rejecting the null hypothesis when the obtained value is large. For statistic t, rejecting the null hypothesis when t is less than minus small t or capital T is greater than small t is equivalent to rejecting the null hypothesis when the absolute value of t is greater than small t. Okay, so this is just reminding people of how absolute values work. Question 15, finish the statistical test and conclude. For this, generate a sample of size 1,000 from the distribution of the absolute statistic. That is to say, compute the distribution of its absolute value, plot the histogram with default parameters, indicate the threshold at 1%, and the value of the observed statistic with vertical lines, compute the p-values of the test. So question 15 is like, do it normally, the way you would do it. Do the histogram, compute the p-value, etc. So we're again going to recompute the null distribution. The only thing is that this time I need to take 1,000, a sample of size 1,000 instead of 10,000. So here we go. I also need to set seed 1 to 3, but I'm just recomputing the statistic that I had before, just for the purpose of following here what they ask. Now, I want to take the absolute value of the null distribution. It's going to be almost the same as the one we had before, except that the sample size is a bit smaller, 1,000 instead of 10,000, a lot smaller. So that's the absolute value here. And now we need to take the statistic of the sample, like really the one that we have observed in reality. Remember there was PO here. So I do statistic PO. I get minus 1.059. So now the question is, So of course that's absolute of that. I need to compare that to what I have on this distribution. I'm now finally comparing the sample, the experimental sample, with what my expectations are. Those are my expectations here. Finally, this null distribution. I have to indicate the threshold at 1%. So that's usually done with quantile. I do quantile here. Oops. At 0.99. Again, I had to take the absolute value here. Oh, it's not this, that's LD. It's 4.48. Of course, not this at all. I have already computed the statistic. So that's the one here, 0.9528. If I do here that, I see that this is my threshold at 1%, meaning that 1% of the probability is here. Now, my observed statistic is this one, 1.05. So I placed it in blue. Oops, blue. It's here. It's on the right side of the threshold. So first of all, do we reject or do we accept the null hypothesis? Anyone? So Dana wants to reject. Anyone else thinks we should reject? Mark also thinks we reject. Yeah, of course. The observed value is more extreme on the right of the threshold, so we reject, which means that it does not look at all like this is the result of a chemical reaction. The variation, even though that was very difficult in the beginning to decide, or indeed sufficient to know that the P2O ratio is indeed different when you put malonate. Okay, that's good. We need to finish by computing the p-value. Does anyone remember how we compute the p-value? P-value, that'd be, well, I need to count basically the blue area in last week's nomenclature, in this sense, which is the area which is from the blue line onward to the right. And so the way we do this is that mean of null d greater than or equal to the blue line here. And p-val is 0.004. That's the answer here, that's the p-value. So we reject the null hypothesis. The deviation is on average, or on effect size, strong enough so that we can be sure at 1% that this is not 1.48. So the answer is the p-value on the quarkus. There are two ways to be wrong when performing a statistical test. The first is to reject the null hypothesis when it is true, and the second is to accept it when it is false. Okay, like you have to make a yes/no decision. Even the answer is yes and you say no, or the answer is no and you say yes. Otherwise, when you say yes and the answer is yes, you're right. When the answer is no and you say no, you're right. So those are called type 1 and type 2 errors, respectively. The level of a test is the probability of a type 1 error. So when you say level, you can also say type 1 error, means the same thing. What is the probability of a type 2 error? There is no single answer to this question because there are multiple ways for the null hypothesis to be false. In our case, we are interested in whether mu is equal to 1.48, and the probability of a type 2 error depends on the value of mu that is different from 1.48. Okay, like there's only one way for the null hypothesis to be true. We're specifying enough information in general for the null hypothesis to be true. Today we have seen that this is not exactly the case, in the sense that we specify mu, but we don't specify sigma. Still, we find a statistic that does not depend on sigma, so it says you just have to tell me mu, and I can compute my expectations thanks to our usual protocol, and that's all I need. So there's only one way, again, for the null hypothesis to be true, that mu is equal to 1.48, because that gives one null distribution for the statistic. Okay, but when it's false, you say mu is not equal to 1.48, well, it could be 1.42, could be minus 15, could be pi, could be 300, could be anything. There's really many ways now in which mu can be inexact. It can be different from 1.48, or whether the null hypothesis can be false. And for each value of mu, the distribution that we're going to get for the statistic is going to be different. So there's not a single answer to that question. If we have set our thresholds, we say now we have our decision rule, which is we compute the statistic the way we did it here, statistic of the sample, and we compare it to our target value, which is 0.95. And you say either the statistic is greater than 0.95 or it's not. If it's greater, I reject. If it's smaller, I accept. That's it. Like my test has been, it's finished. I have the decision rule, that's the step 5, and that's the final stage there. So now the problem is, if mu is inexact, I still have exactly the same protocol. My protocol hasn't changed. Now what I need to know is that when mu is false, what is the probability that the statistic is on the right or on the left? Because my decision is just based on that. And well, that depends on what mu actually is. So assume mu equals 1.48 plus sigma, and therefore the null hypothesis is false. Set the variable sigma to any value except 1, and draw a random sample of the statistic from a population of 11 measurements with this assumption. Change the value of sigma and reset the random seed. Does the value of sigma have any influence? Okay, so here we go. It says take our norm, n equals 11, as usual. We're just simulating the process that we're generating the same data set. And then mu, so mean equals 1.48, and SD equals sigma. So mu is 1.48 plus sigma. So that gives us here a couple of Gaussian random samples that are conditioned by having the mean, which is not 1.48, it's 1.48 plus sigma, but sigma is still the standard deviation here. And on this, I can, of course, compute the statistic. So now this is not the null distribution anymore. Okay, when I sample from this distribution, because the mean is not the correct one, then this is not the null distribution. The null hypothesis is false here. But I'm computing the distribution of the statistic when mu is 148 plus sigma. So when the null hypothesis is false. So change the value of sigma and reset the random seed. Does the value of sigma have any influence? So here we go. We can, for example, do set seed 1, 2, 3. So the number is 1.21. That's good. The sigma was 182.7. I'm going to say sigma is 1.827. Reset the random seed. And when I do it again, then I got exactly the same result. Okay, so basically my null hypothesis here is false, but doesn't matter what value of sigma is the true one. Here, that that distribution that I'm going to draw does not depend on sigma again. Okay, so that will allow me to make a distribution of the statistic when the null hypothesis is false in that specific way. That mu is 1.48 plus sigma. Okay, so I'm going to make a distribution of that in this particular case. And again, I arrange myself so that it doesn't matter what sigma is, the result will always be the same. So using replicate, generate 1,000 random values of the statistic. In this case, when mu equals 1.48 plus sigma, symmetrize the statistic by taking the absolute value and plot the histogram using default parameters. So basically, we have to do this and put this into a replicate statement, n equals 1,000. So that will compute the value of the distribution. So that's not the null distribution, that's the alternative distribution, alt d. It's this, but we're going to set seed 1 to 3. And if I do the histogram of the absolute value of alt d, this is what I get. Okay, you see that it looks very different from the null distribution. The values around 0 are not that frequent. Well, that's normal. Like, remember, like, we have made the null hypothesis in such a way that, and the score, in such a way that when the statistic is 0, then it speaks in favor of the null hypothesis. And when the statistic is away from 0, higher than 0 because we take the absolute value, then it speaks against the null hypothesis. So yeah, sure, that's reassuring in the sense that when we assume that the null hypothesis is false, like mu equals 1.48, then the probability of getting something close to 0 is not that big. We're not going to conclude that the null hypothesis is correct when in reality it is not. We are shifting the average of the distribution away from 0. So that's a very different outlook compared to the other ones that were starting with a high value at 0 and then going down. So that's normal. Compare the histogram to that of the null distribution, so they're very different. What range of values has the highest frequency? So this time it's the values between 1 and 1.5. It's not the values around 0. And again, that's what I said. We violate the null hypothesis. Therefore, the distribution of the statistic is not going to be close to 0. Call T the threshold at level 1%, taken from the null distribution at question 15. So that's the value that was 0.95 was above here. That's T here. So call T the threshold at level 1%, taken from the null distribution in question 15. What is the probability that the statistic is greater than equal to T when the null hypothesis is false with in that way? Is this probability greater or smaller than when mu equals 1.48? So the probability that the score in the alternative distribution is greater than or equal to T is 0.591. That's the answer to the question. So is that greater or smaller than when the null hypothesis is false? What do you guys think? What was it again when the null hypothesis was true? It was 1% by definition. Okay, so we went from 1% to 60%. So yeah, that's bigger, that's much bigger. And of course, here it's because the threshold is somewhere around here. Okay, and you have 60% chance of being on the right side now because, yeah, the null hypothesis is false. Therefore, the score is expected to be higher. And that probability here that the threshold is kind of, that the observed statistic is beyond the threshold is of course much higher by construction. Based on your answer at question 18, give an estimation of the probability of type 2 error when mu is equal to 1.48 plus sigma. Well, this is 1 minus that. Okay, so because we're rejecting with almost 60% of the time, but we're right to reject when the null hypothesis is false. So we're wrong 40% of the time. So that is the answer to question 19. Well, we're going to stop here. Time's up. So you still have question 20 to finish. And you can, if you're interested, look at section 7. But that's it for today. And I think that will give you just a small amount of work before the midterm. And I will open the quiz on the Quarkus right now. Thank you for your attention and see you soon.